going to go through an application of how to use integration and particle motion problems. So here is an example that you see a lot in textbooks. Really helps you understand the concept of integration and how it relates with differentiation and so on and so forth. So what we have here is f is a differentiable function whose graph is shown in this figure. So here's the figure of f. The position of time t seconds of a particle moving along a coordinate axis is given by this in meters. Key thing that you have to realize, and you have to know, is right here, I'm going to highlight this, is that this right here stands for what? All right. Now, some of you may say, I don't know. Well, this right here, this is our position function. All right. So when we integrate f, all right, right here, we are given a position function. So knowing that, what does f, this graph right here, have to do with s? Well, f is actually equal to the derivative of s, which means if this is a position function, what the derivative of a position function means you are finding the velocity function. So yes, f is actually equal to the velocity function. That is important to know. And whenever you're given a graph, all right, and an integral, it's important to identify what is everything significant, or what everything stands for. So s is an antiderivative of f, which we don't know, all right, but we do know that s, all right, that f right here, these are all the velocities of our function, our position function, which is f right here, and it's in meters. Okay, so let's go through this and try to figure this stuff out. All right, so what is the particle's velocity at t equals 5? Well, since s prime equals f, which equals velocity, we know we can figure this out by just simply taking s prime of 5, which will equal f of 5. And what we have is, looking at this, since f of 5 is our velocity, f of 5 equals 2, so it'll be 2 meters per second. And that would be our answer. Easy, right? Now, next one we have acceleration. What is the acceleration of the particle at t equals 5? Is it positive or negative? So here, acceleration, if we recall, acceleration is the derivative of the velocity function, which in this case would be the derivative of our f function. Well, if acceleration is positive, that means, what do we know about f? Well, f prime has to be positive, greater than 0, if it's going to be positive, or it's going to have to be less than, or it's going to be negative. Well, in order to help us figure this out, what we can kind of think about is this, is that f, if f is increasing, then we know that f prime, which is our acceleration, should be positive. If f is decreasing, all right, then f prime will be negative, all right, which is our acceleration. So let's look at 5. And on this interval between here and here, we realize that our values are decreasing. It is decreasing. So f is decreasing at 5. So this is what satisfies that. So guess what? Our values are going to be negative, and that's the reason why. All right, let's continue on. What is the particle's position at t equals 3? All right, position. All right, if we're looking for position, we're looking for s of 3. Well, s of 3 is going to be equivalent to the integral of f. So s of 3 from 0, and since our time is 3, we're going to plug in 3 up here, and we're going to take f of x dx. Well, to find s of 3, we're going to take the integral of this. Integral is an antiderivative, well, we're not given the function. So how else can we find the value of s of 3, and how else we can find the integral? If we recall, integration is also finding the area of the curve. So to find s of 3, I guess we're going to assume that s of 0 is 0. Starts at the origin. And what we're going to do is we're going to integrate this. That means we're going to find the area from 0 to 3 of this function. And by doing so, hopefully we can use some geometry. Don't have to use any Riemann sums or anything. But what we have right here is, yes, this right here is the area, which is a triangle. So we're going to take 1/2, the base, which is 3, times the height, which we know is 3. And so our answer is going to be 9 halves. meters is going to be our particle position at t equals 3. Okay. Hopefully this is starting to make a lot of sense to you. Let's continue on. At what time during the first 9 seconds does it have the largest value? S have the largest value. So where is it going to be S have the largest value? Well, in doing this, normally what we would do is we go S prime. All right, try to find the zeros, and we're looking for the largest, which means we're looking for a max. So we're trying to figure out when S prime equals 0 and where S prime changes from positive to negative. Changes from positive to negative. All right, now where does this occur? Well, our velocity right here is going to be positive, and here we have our 0. And here it changed from positive to negative. So right here, we're going to have t equaling 6 is going to be our largest value. Okay, so t equal at t 6 seconds, that's where we're going to have our largest value. All right, let's keep on going through and let's see what the next one is. Approximate when the acceleration is 0. Well, acceleration, all right, is s double prime, which means we need the derivative of the velocity function, and that equals acceleration. Well, velocity is f, so basically we're looking for the derivative of f. Now, the f prime is, since we have this, we're looking for horizontal tangents. Horizontal tangents. All right, horizontal tangents usually occur at max and min. So if we look at this, when does f have a max or min? Well, that appears to be occurring here and here. So we'll estimate this to be at 4, t equaling 4, and t equaling 7. All right, and that's going to be where we have horizontal tangents, and that's when all this will be taking place. All right. Finally, the last couple. When is a particle moving toward the origin? Toward the origin. Now, toward the origin means when the velocity is positive. All right, the velocity. Toward the origin means when the velocity is negative. So toward means it's going to be lesser. So velocity is going to be negative, which is our v, has to be negative. So when is our velocity or v negative? Well, our v is negative from 6 to 9. So on the interval from 6 to 9, all right, our particle is moving toward the origin. However, when we go right here, moving away from the origin means it's getting farther away. So that means it's when the velocity, or in this case, f, is going to be greater than 0, and that occurs from 0 all the way to 6. All right, so we're going to go from 0 to 6, and that is when the particle moves away from the origin. Okay, our final concept that we want to try to answer here is this. On which side of the origin does the particle lie when t equals 9? Oh boy, okay, let's see if we can figure this out. Well, to figure this out, I'm going to erase this here. We want to figure out what is happening to our position. Well, right here, we want to figure out what is the integral, all right, if it's going to be positive, so from 0 to 9, if the integral of f of t, which equals s, is going to be positive, or is it going to be negative? All right, positive or negative. All right, positive or negative. So to figure this out, we have to identify what is happening to each one of the areas. Well, we know that the area above the x-axis, which we see right here, is the integral from 0 to 6, all right, of f of t. That this area appears, and I would probably say, you could say, that this area is going to be much greater than the area that is going to be negative. And the area that's negative, we know, is below the x-axis from 6 to 9 of f of t dt. And we're going to take the absolute value of that so that we know that both these areas will always be positive, but this area, which is positive, will always be larger than the area that's negative. Since this is true, since the area that is positive is greater than the area that's negative, that means if we add the integral from 0 to 6 of f of t dt, our positive area, which is greater, and add that to the integral from 6 to 9 of a smaller area that is negative, that means that this right here will have to be greater than 0, which means then the integral from 0 to 9 will have to definitely be greater than 0. And on which side does that lie then? Because this is greater than 0, it's going to lie on the right side of the origin. All right. Well, with that, we have just completed one particle motion problem that hopefully will help you solve many on the AP test for response questions, also hopefully on your homework. It's going through how to figure out what does S mean and how does that relate with the integral of a function f. Key things, once again, really understand what is the graph represent and how does that relate with the integral and the position function. All right, well, hope this helps you out. Good luck and God bless in the rest of your problems.